In this next lecture, we're going to go over the basic functions of an anesthesia machine and walk through how to set the anesthesia machine up in order to use the Supernova device. Although the anesthesia machine is a very complicated device, we only need to know two basic functions in order for the Supernova to work properly. The first is how to deliver oxygen to the patient. The second is how to mechanically ventilate the patient using the anesthesia machine. The first thing you need to do is make sure that the oxygen is turned on. In order to do so, look on the anesthesia machine. Shown here in green indicates oxygen. This is known as the flow meter. In order to ventilate a patient, we need to build up a positive pressure. So how do we do that? Well, pressure is equal to flow times resistance. The flow is obtained by oxygen. By turning the flow meter up, we are generating a continuous flow of oxygen that is going to the patient. Now, since flow is directly proportional to pressure, the higher the flows, the more pressure. So, for example, 10 liters per minute of oxygen is going to give you a higher pressure delivering to the patient than 1 liter per minute. Next, we need to create resistance. In order to do so, we need a closed system so that gas cannot leak into the atmosphere. For example, the Supernova, when placed firmly over the patient's face, creates a closed system by its seal. Now, the resistance within the system is going to be inversely proportional to the diameter of the tube through which oxygen is flowing. For example, the anesthesia circuit would be the smallest diameter. Therefore, the resistance is going to be equal to that tube. If you want to increase resistance, what you would have to do is you would essentially decrease the diameter of the tube. An example of this is it's a lot harder to breathe through a pediatric endotracheal tube as compared to an adult endotracheal tube. And the reason is obviously because the tube diameter is smaller for the pediatric size, which creates more resistance. Therefore, you need a higher pressure in order to ventilate through it. There are two ways that the mechanical ventilator can actually generate pressure. One is through manual mode ventilation. This is where the clinician actually sets the pressure, which will go into the next slide, where you use the anesthesia machine's APL valve or pop-off valve in order to regulate how much pressure is going into the patient. The second way is by automatically ventilating the patient via a mechanical ventilator, which is built into the anesthesia machine. With the mechanical ventilator, the clinician sets that pressure that will be delivered to the patient. Let's first go over how to increase pressure through manual ventilation. This is when the clinician actually bag masks the patient. In order to determine the amount of pressure that's delivered, the clinician is going to first increase the oxygen flow meter. Then he's going to adjust the pop-off valve as shown here. The pop-off valve is essentially the opening that the patient exhales against. Now, the size of that opening determines how much resistance the patient is breathing against, and therefore how much pressure is built up in the system. The range of the pop-off valve is between 0 and 70 centimeters of water pressure. You can change the resistance, or change the pressure by adjusting or turning the pop-off valve. At 0 centimeters of water pressure, that valve is completely open, which means the patient is breathing against no resistance, and therefore no pressure will be built up. At 70 centimeters of water pressure, that valve is now completely closed. So the patient is breathing out against something that will not let them breathe out because it's closed. Therefore, the pressure will continue to rise. Typically, the pressure to set for nasal CPAP is between 10 and 20 centimeters of water pressure. The pressure for nasal ventilation should be set between 20 and 30 centimeters of water pressure. As you can see in this picture, the pop-off valve is set at 30 centimeters of water pressure, which means that there will be 30 centimeters of water pressure built up
within the patient's nasopharynx and the patient's lungs, assuming there are no leaks in the system. For mechanical ventilation, the clinician first has to set the amount of pressure they want to deliver to the patient. As you can see here in this arrow, this is where we would set the pressure. It is then the mechanical ventilator that actually generates the pressure that is delivered to the patient. There are 4 main settings on the ventilator that you should know what the setting means and what its average ranges are. Let's first start with tidal volume. This is the amount of volume that a patient inhales and exhales with natural breathing, i.e. not taking a deep breath. On average, a tidal volume should be between 6 and 10 milliliters per kilogram. So that means about 450 to 750 mLs per breath. Next, you should know what the respiratory rate means. This is the number of breaths a patient takes per minute. On average, the normal patient should be able to take 8 to 14 breaths per minute. You also need to know pressure. This is a setting on the ventilator where we can set what pressure we want the mechanical ventilator to deliver to the patient for each breath. The highest amount of pressure that is really recommended is usually between 30 and 35 centimeters of water pressure. However, the average pressure that should be delivered is only between 10 and 30 centimeters of water pressure. Anything above this places the patient at risk for lung injury known as barotrauma. Finally, you need to know what positive end expiratory pressure is. This is also known as PEEP. PEEP is the pressure that the patient has to exhale against. It's essentially a back pressure. Back pressure is used for 2 things. 1, it helps keep an airway stented open, and it helps keep the alveoli open, or it prevents them from collapsing. The average PEEP is about 5 centimeters of water pressure. However, patients that either have obstructive sleep apnea or are obese may require pressures of even 15 centimeters of water pressure. All 4 of these ventilator settings, again, you need to be familiar with and know their average ranges so that you can recommend to the clinician how they should set their ventilator settings when using the Supernova. Next, let's go over where those 4 main settings may be located on a mechanical ventilator. This is an Apollo dragger. Not all of the anesthesia machines that you will encounter will be Apollo draggers. However, the settings are typically located in the same place. Here, as we see at the bottom, we have a pressure max of centimeters of water. This is where you would set the pressure that you would want delivered to the patient. Right next to it is VTML. This stands for tidal volume, or the volume that you will be delivering to the patient. Remember, it should be around 450 to 750 mLs. Right next to it is the frequency. BPM means breaths per minute. This is your respiratory rate, which should be set between 8 and 14 breaths per minute. Finally, over here is PEEP. Again, typically set between 5 and 15 centimeters of water pressure. You also need to be familiar with the different modes of mechanical ventilation. Now, there are 2 basic modes. We have spontaneous ventilation modes and controlled ventilation modes. Let's first start off with what are spontaneous ventilation modes. This is the mode where actually the patient has to be breathing on their own, or they have to initiate their own breath. What the ventilator does, it then adds additional support to that breath. For example, say I can take a pressure of about 10 centimeters of water pressure. However, in order for me to maintain effective ventilation, I may need 20 centimeters of water pressure. What I can do is I can ask the ventilator to add an additional 10 centimeters of water pressure to every breath that I take. Now, that 10 centimeters of water pressure that I generate, there will be an additional 10 centimeters of water pressure provided by the ventilator, which in total, I will get a pressure of 20 centimeters of water pressure. Again, let's summarize. Spontaneous ventilation modes, the patient has to be breathing on their own, and they get additional support from the mechanical ventilator. Next, let's go over controlled ventilation modes. This is when the ventilator is completely controlling the number of breaths and either volume or pressure being delivered to the patient. What that means is that the patient does not have to be breathing on their own. Essentially, the mechanical ventilator is generating either enough volume or pressure to take over the breathing for the patient. So in summary, controlled ventilation, the clinician sets the rate of breaths to be delivered to the patient and will set either the volume or pressure that is delivered to the patient. Let's take a more in-depth look at spontaneous ventilation modes. Now there are two basic modes. The first is pressure support ventilation, also known as PSV. If you remember, in order for spontaneous ventilation modes to work, the patient has to be able to initiate their own breath. The ventilator then delivers a preset additional pressure. The reason for this is to try and help maintain effective ventilation or increase the tidal volume that the patient is getting. This will help decrease the risk of atelectasis. If you remember, in order to prevent atelectasis, we need all of our alveoli to open. We do that by taking a deep breath. However, with sedation medications, that causes us to take shallow breaths. In order to compensate for that, the ventilator can add additional pressure per breath in order to increase those tidal volumes and open all of the alveoli. For example, say I can only inhale at a pressure of 10 centimeters of water pressure. However, in order to open up all of my alveoli, they require 20 centimeters of water pressure. We can set on pressure support ventilation mode a pressure of 10 centimeters of water pressure. This will now add an additional 10 centimeters of water pressure per breath. When you add my 10 that I can already take to the ventilator's 10, that gives us 20 centimeters of water pressure, which allows for all my alveoli to open up. The next mode is pressure support with positive end expiratory pressure. This is also known as BiPAP. Essentially, this mode is pressure support ventilation with adding an additional expiratory pressure. BiPAP allows us to regulate both the inspiratory pressure and independently the expiratory pressure. For example, maybe I only need 10 centimeters of additional pressure on inspiration, but on expiration, I only need 5 centimeters of water pressure. We can now set the ventilator to give me an inspiratory pressure of 10 and an expiratory pressure of 5. The expiratory pressure allows for two things. One, it applies a back pressure, which can help stent open my upper airway obstruction. Also, it can apply that back pressure to my lungs and help stent open my alveoli even as I'm expiring. This also helps prevent atelectasis. Let's take a more in-depth look at controlled ventilation modes. Just to recall, it's called controlled ventilation because the clinician is setting the ventilator to completely control either your pressure or volume delivered and the amount of breaths the patient receives per minute, i.e., the clinician is completely controlling how much ventilation is being delivered to the patient. Now, there are two types of controlled ventilation that you'll need to know. The first is pressure control, and the second is volume control. Let's go over what those mean. Pressure controlled ventilation means the clinician presets how much pressure they want delivered to the patient per breath. For example, let's say the clinician wants 20 centimeters of water pressure. They will then set the ventilator to 20 centimeters of water pressure. What pressure control cannot control is the amount of volume delivered to the patient. The ventilator will continue to increase the amount of flow delivered to the patient until 20 centimeters of water pressure is reached, at which point it'll allow for exhalation. Next, let's go over volume control ventilation. This is where the clinician presets the amount of volume delivered to the patient per breath. For example, the clinician may set 500 milliliters per breath. Therefore, volume control cannot control how much pressure is being delivered to the patient. What that means, the ventilator will continue to try and deliver 500 milliliters is delivered to the patient. So in summary, pressure control ventilation, the clinician sets the pressure. The pressure is the only thing that is being controlled, not the amount of volume delivered to the patient. Volume control ventilation, the clinician sets the volume.